basic video covering hypothesis tests in section 10.2, the difference of two means. I'm just going to focus on one example problem here. I'm going to do a separate video just working through one more example problem, just give you a little bit more exposure, but we're going to run this through at a pretty high level. So in the hypothesis concept test, we're going to start with the general theory that the two means are the same. So the difference of the two means will be 0. That's going to be your standard null hypothesis whenever we're doing any of the two sample difference of means analysis. Our alternative hypothesis will be our classic two-sided. Hey, the means are not the same. They're just, the difference is not equal to 0. But then we'll look at two other conditions. We'll look at the condition where the difference is positive, which also translates into, and let me just go ahead and put this over here. This translates into mu1 greater than mu2. Or we might also see the other situation. Our alternative is mu1 minus mu2 is less than 0, which translates into mu1 is less than mu2. And you'll see that when we talk about some of the calculator pieces potentially. So, as before, we're going to work with a t-statistic as I throw my pen around. And what's that t-statistic going to be? Well, it's going to be the difference of your two sample means minus, again, remember, we're getting a t-value just like we used to get a z-score. We can call this a t-score if you like. That's fine with me. Minus mu1 minus mu2. And then what are we going to do? Divide by the standard error. Standard deviation of the first sample squared divided by the sample size, plus the same thing for the second sample. And again, all square rooted. Remember, variances add, sample variances add. In this case, since we're working with a mean, we'll divide both those variances using our old principles before by the associated sample size. So that lovely thing in red, just one big square root, and that'll translate into just what you see right below here. Remember, because mu1 minus mu2 is nothing more than 0 because of the fact that in the null hypothesis we say they're equal to each other. We'll get our t-statistic. We'll compute our p-value. And just like I said in the other case, if we're going to go ahead and kind of do this manually or quasi-manually without the true calculator test is maybe a better way to say that. Well, what will we do? Well, we'll use a TCDF, and our degrees of freedom, again, will be the smaller of the two sample sizes minus 1. So that's kind of how we'll go ahead. Then we can do a TCDF off of our t-value to come up with our appropriate p-value, track that against our alpha level, our significance level, and go ahead and make our reject null hypothesis, fail to reject null hypothesis decision. And we'll see on the calculator there'll be a 2-samp t-test. It does something much more sophisticated. Again, you will never have to do this by hand. It does something much more sophisticated with the degrees of freedom to come up with what I guess you could say is a more precise versus our slightly conservative, but nonetheless still effective estimation in terms of how we work with those degrees of freedom. So, all that preamble done, we're going to talk about example number 8. How quickly do synthetic fabrics such as polyester decay in landfills? This is one of the check your understanding problems in the book. So it's a good one to work through, just in the fact that it wasn't actually worked out in the textbook. So you'll have other examples to kind of study from. So what's looked here is this thing called breaking strength. And breaking strength just basically is an indication of how much force you have to do on the fabric to break it apart. The higher your breaking strength is, the harder it is for you to tear the fabric apart. That means it hasn't decayed as much. And so we're going to compare breaking strength at 2 weeks and 16 weeks and see if there is a difference. In this case, do we have convincing evidence that polyester decays more in 16 weeks than in 2 weeks? That should mean that the breaking strength in 2 weeks is higher than the breaking strength at 16 weeks. So kind of keep that in mind. So all that out of the way. Go find where I did my work. Now, let's talk about a couple conditions. I'll do that a little bit lower here than usually I would like to, but that's fine. We'll just kind of put it here. Do I have a random experiment? This is the nice thing here. 10% rule really doesn't apply because I have randomization in the context of working with an experiment. I've taken these pieces of fabric and I've thrown them into, kind of two treatment bins, the 16-week treatment bin, the 2-week treatment bin. That's been done randomly. So I do have some of the random conditions that I need. Again, because it's an experiment, one of the nice things, you'll have to read a little bit more on this as you go through some of our examples. We kind of get lucky here. I don't have to worry about the 10% of the population rule for what I'm doing here. I only have a sample size of 5 for both of these 16-week and 2-week polyester bins. That's not bigger than 30. I have no central limit to hang my hat on, so what do I need to do? I need to manually inspect my data. Manually, what am I saying? Go ahead and put it into L1, L2. Let your calculator do all the work. And just to save ourselves just a little bit of time, you can do this very quickly, I think. If you put those 5 values that we had, for each of these 2 different samples of 5, we would see that there are no strong outliers. There's no real skewing. The data's relatively okay. What does that mean? Relatively okay. Poor term. There's nothing that suggests that this data is not normally distributed. That's a much better way of saying that. And because of this, that'll allow us to go ahead and run a t-test. Again, why a t-test? Because we have no idea the true population standard deviation. So we'll run a t-test. We'll do so at an alpha level of 0.05 at 5%. So let's pull a couple things. Here comes all our data that we would have gotten out of the calculator. Oops, my fault. Let's get this other piece of paper out of the way. It's an earlier problem. My 2 weeks, I can see my X bar. I can see my sample standard deviation of 4.6, sample size 5. For my 16 weeks, 116.4 was the mean breaking strength. 16.09 was the sample standard deviation. Again, sample size of 5. Our null hypothesis, I'm going to go with 2 weeks. I'll use subscript 1, 16 weeks, subscript 2. Null hypothesis is what? Mu1 minus mu2 equals 0. 2 weeks and 16 weeks have the same decay, and maybe more specifically have same breaking strength. I was going to write BS, but that wouldn't have been good. They'll have the same breaking strength. What's my alternative hypothesis? Well, I'm hoping that 2 weeks has a higher breaking strength. Remember, higher breaking strength means less decay. And so I would be hoping that mu1 minus mu2 is greater than 0. That's my alternative hypothesis based on just kind of the normal suspicion. Hey, it hasn't decayed as much in 2 weeks as it will in 16 weeks. So there's all my work. Let's go ahead and set up the number crunch part. Here comes my t-value, 123.8 minus 116.4 minus mu1 minus mu2. Again, that's a good old 0. And then here comes my good old standard error for this data, 4.6 squared over 5 plus 16.09 squared over 5. And when all things are out, do a little bit of rounding, I'll have 7.4 over 7.484. Run that through, go to 3 decimal points, and I have a t-value of 0.989. Now, what am I looking to? I'm looking to do a right-sided, one-tail right-sided t-test here. I'm going to look for the probability that if my t-distribution would have brought back a standardized t-value of 0.989 or greater with a degree of freedom of 4. How do I do that in my calculator? Okay, I wrote the degree of freedom one more time. Here's my p-value, TCDF. You can see my lower, my upper, as far out as I can go, degrees of freedom 4, and I come back with a p-value of 0.189, 18.9, almost 19%. Since that value is much greater than 0.5, I don't have sufficient evidence to reject H0. I'm going to fail to reject H0. I do not have significant enough evidence to believe that the decay rate is any different between the 16 weeks and the 2 weeks. And that's kind of how we would work our way through this problem. Now, one more thing just to show you. Go to my calculator. How could I do this more directly? Right straight through the calculator. Again, you'd have to show all this, but what would the calculator come up with a value? You see their end result. Well, let me take you all the way back to the beginning. Stat, test, and I'm going to look at my 2-samp t-test. Choose it, and here comes all my work. Here's my data. I'm going to work from stats. Could I have worked from an L1, L2? Could have done all that as a matter of fact, but right now I'll just manually input all the data. You can see my first 3 fields, the 123.8, the 4.6, and the 5, came from what? The 2 weeks value. Here comes my 116.4, 1609, and the 5 for my 16-week sample of 5. I'm asked what's my null hypothesis, And you'll see that I've chosen the what? Greater than. That's the right-hand side. Remember, what am I looking for? I'm under the assumption that mu1, excuse me, here we go. Mu1 is what? Minus u2 is greater than 0, which means that mu1 is greater than mu2. And so that's what you see put in as the choice that I've made for our alternative hypothesis. For the moment, again, if you're asked pooled data, no. Go ahead and calculate. Slide my calculator down, and you'll see all the key things. You'll see the t-value that came up, 0.9887, 0.989, kind of was my round. And what do we get for the more precise? 0.1856. I had what? 0.189 as my manual value here, again, because it's a rounding and stuff. And then also the one other key piece. Remember that complicated formula that you read about that you don't need to remember or use? Haha. What do you see? A degree of freedom here. Rather than the conservative value of 4 that I provided, it'll actually be the true precise 4.649 blah, blah, blah. And that's why we get a slightly different answer off the calculator than we did just kind of with our rounding and conservative approach. So this is the bottom line, just working through example 8, the confidence intervals we did in part 1. Here we did t-test, a hypothesis, 2-sample t-test. And I think this will give you a good start. I'm going to make a separate video with one more example problem, just so you have something to work with. I'm going to assign one homework problem to you associated with this video as well. Thanks.